Sit down with a blank sheet of paper and start drawing. 2 parents at the top, 4 grandparents above them, 8 great-grandparents above those, and keep going, doubling every row. The paper runs out long before the family does. 40 rows up, 1,000 years, give or take. That sheet's asking you to name 1,099,511,000,000 people, every one of them a separate human being with a separate life. The number isn't an exaggeration or a rounding. It's exactly what your own family tree demands of history. And it can't possibly be true, because it's more than 9 times the number of human beings who have ever been born. Both of those statements are correct. That's the problem this video is about. The arithmetic isn't in dispute, and neither is the population figure. They simply can't be reconciled by any ordinary reading of what a family tree is. Somewhere between the second row of that page and the 40th, something happens that nobody explains when they hand you a blank pedigree chart or a subscription to a genealogy site. The people you're looking for aren't missing. They were never as numerous as the diagram claims. There's a second consequence, and it lands on anyone who has spent years building one of these charts. It arrives about 800 years up, and it's the reason professional genealogists disagree about how deep a family tree is worth taking. Start with the part that behaves. 2 parents, then 4 grandparents, then 8 great-grandparents, and 16 above those. At the 10th generation, the chart calls for 1,024 separate people, and using the best current estimate of how long a human generation runs, 26.9 years, from a 2023 study in Science Advances that measured generation times across the past 250,000 years, that 10th row lands somewhere around the year 1757. 1,000 ancestors in the 1750s. That's already more names than almost any family has ever documented. But there's nothing impossible about it. There were plenty of people alive in 1757. Keep going. 20 generations back, the chart wants 1,048,576 people, and the year is roughly 1488. Still no contradiction. The world had a few 100 million people in it. 1 million ancestors is a large slice of Europe, but it's a slice, not the whole. The trouble starts on the next stretch, and it starts fast. 29 generations back, around the year 1245, the chart demands 536,870,912 ancestors. One more row, generation 30, roughly 800 years ago, about the year 1219, and the figure passes 1,073,000,000. There weren't 1 billion people on Earth in 1219. Estimates for the medieval world population vary by demographer, and the honest range for that era is somewhere between 250 and 400 million. Take the most generous of those numbers, and your family tree, at generation 30, is asking for roughly 2.5 times every human being alive on the planet. Not 2.5 times the people in your country, 2.5 times the species. That's where the diagram first breaks, and it breaks 8 centuries ago, recent enough that many of the parish registers from either side of the gap are still sitting in archives today. Push on to generation 40, and the mismatch stops being a mismatch and turns into something closer to absurd. 1.1 trillion ancestors, around the year 950, against a world of perhaps 400 million. The tree's demanding roughly 2,700 people for everyone who is actually alive. Set the medieval world aside for a moment and measure it against everybody instead. The Population Reference Bureau maintains the standard estimate of how many members of our species have ever been born. Built by the demographer Carl Haub in 1995 and revised with Toshiko Kaneda in 2022, that model produces a figure of about 117 billion people, every human who has ever drawn breath, from the earliest anatomically modern populations through everyone reading this sentence. The 8 billion of us alive right now are roughly 7 out of every 100 people who have ever existed. 117 billion total. Your tree at generation 40 wants 1.1 trillion. It's short by a factor of 9. Your family tree, extended a single millennium, requires 9 times more human beings than have ever lived, and it needs all of them inside 1,000 years rather than 300,000. To get a feel for the size of the demand, If you sat down and named one of those ancestors every second, without pausing to eat or sleep, you would finish in about 35,000 years. That is the shape of the claim your pedigree chart quietly makes on your behalf every time you draw one more row. So the number is wrong. The question is which part of it is wrong, and the obvious answers all fail. The first instinct is that the records are incomplete. They are, badly so. But that doesn't touch this at all. The arithmetic never depended on records. It comes from a single assumption everyone accepts without examining, that each person has two parents. Nobody's ever found an exception. The doubling isn't an estimate that better archives could correct. The second instinct is that the maths is somehow wrong. It isn't. 2 to the 40th power is 1,099,511,627,776, and it'll be that number tomorrow. The third instinct is the interesting one, that people simply had fewer children back then, or died younger, so the population was different from what demographers think. But that reasoning runs the wrong direction. Making the medieval world smaller makes the gap wider, not narrower. There's a fourth attempt worth retiring while we're here, because it's the one people reach for last. Perhaps the generation length is off. Perhaps people married later, so 1,000 years covers fewer rows. Stretch the generation all the way to 33 years, which is longer than any serious estimate for pre-modern populations, and a millennium still buys you 30 rows. 30 rows is still 1,073,000,000 ancestors, and there still weren't a billion people alive to fill them. The assumption you'd have to break to save the tree isn't the timing, it's the tree. Every explanation that keeps the tree a tree fails, which means the tree is the thing that has to give. There is one family in European history that documented the whole process happening to them, generation by generation, and left the paperwork in an archive. Hold that thought, because the mechanism has to come first, or their story is just a curiosity about royalty. Here's what's actually happening. That chart has 1 trillion slots on it. What it doesn't have anywhere is 1 trillion separate people to put in them. Those are different quantities, and the difference is the entire answer. A slot is a position. Your father's father's mother, 40 rows up. Every slot is genuinely occupied by a real ancestor. But nothing stops one person from occupying many slots at once. If 2 of your great-great-grandparents were second cousins, and across most of human history, in most places, they very often were, then they shared a set of great-grandparents, and those people appear in your chart twice. Not as an error, as a fact. Go back far enough, and this happens constantly, everywhere, in every line. The chart keeps doubling because the chart can't count. The population of distinct human beings behind it stops growing, folds back on itself, and begins repeating. Geneticists call it pedigree collapse. Your family tree stops being a tree at some point in the medieval period and becomes a web, a network where lines rejoin, cross, and rejoin again, with the same people sitting in thousands of positions simultaneously. This is worth being precise about, because it's easy to hear pedigree collapse as a polite word for something shameful. It isn't. It doesn't require anything scandalous or even unusual. All it requires is that people married within reach of where they lived, which is what nearly everyone did for nearly all of human history. A village of 400 people, marrying mostly within itself for 3 centuries, produces massive collapse without a single union anyone at the time would have considered close. The mechanism is universal. What varies is the rate. Marry across an ocean and your lines stay distinct longer. Marry across a valley and they rejoin sooner. Which brings back the family that didn't leave any of this to inference. The House of Habsburg ruled Spain and its empire from 1516 until 1700, and for most of that period, they pursued a deliberate policy of marrying relatives, uncle to niece, first cousin to first cousin, to keep territory and titles inside the family. Because they were royalty, every one of those marriages was recorded, dated, and preserved. The result's a pedigree collapse that wasn't inferred or modeled. It was simply written down at the time. In 2009, a team of Spanish geneticists Gonzalo Alvarez, Francisco Ceballos, and Celsa Quintero, published a study in the journal PLOS I that did something nobody had done with the archive before. They reconstructed the genealogy of the dynasty's final king, Charles II, along with 3,000 of his relatives and ancestors, across 16 generations. Then they calculated, for each individual, the inbreeding coefficient, a single number that measures how much of a person's ancestry doubles back on itself. Across the dynasty, that number climbs steadily. Philip I, at the start of the line, sits at 0.025. By the time you reach Charles II, born in 1661, it has reached 0.254. That figure deserves a moment. A child born to a brother and a sister has an inbreeding coefficient of 0.25. Charles II's was higher, and he wasn't the product of anything that extreme. He was the son of an uncle and a niece, several generations into a family that had been doing versions of the same thing for 2 centuries. The compounding did what the single relationship alone never could. His family tree at 16 generations should have contained 65,536 distinct people. It contained a small fraction of that. The slots were full. The people were the same people, over and over. Charles was ill for his entire life. The 2009 study proposes that 2 separate recessive genetic disorders, inherited at unrelated points in the genome, account for most of his medical record: combined pituitary hormone deficiency and a kidney condition called distal renal tubular acidosis. Both are conditions you can't inherit without getting the same rare variant from both parents, which is precisely what a collapsed pedigree makes likely. The same paper calculated that inbreeding at merely the first cousin level cut survival to age 10 by around 18% across the family. When Charles died in 1700 without children, the Spanish Habsburg male line ended. A dynasty that spent 2 centuries marrying inward to hold a family together ran out of family. The Habsburgs are the extreme case, and they were doing it on purpose. Everyone else's ancestors did a gentler version of the same thing without intending anything at all, and the mathematics doesn't care about the intention. It only counts the folds. Once you accept that the lines fold, a second question arrives, and it is the one with real consequences for anyone holding a DNA test. If everybody's tree is folding back on itself, and everybody lived near everybody else, how long before the folds start overlapping between different families? In 2013, Peter Ralph and Graham Coop answered that for Europe with genomes instead of models. Their study run in PLOS Biology. They took genome-wide data from 2,257 people across the continent and looked for long shared stretches of DNA, segments that get chopped shorter every generation by recombination. So a long shared piece means a recent shared ancestor. They found 1.9 million of them. 2 Europeans from neighboring countries turned out to share somewhere between 10 and 50 genetic common ancestors from the last 1,500 years alone. And because the genetic ancestors you can detect are only a small fraction of the genealogical ancestors you actually have, the authors extrapolated to a conclusion that sounds like it must be an overstatement, and isn't. Essentially, everyone living in Europe 1,000 years ago who left any descendants at all is an ancestor of essentially every European alive today. Not a common ancestor between some of them. All of them, to all of them, from Portugal to Poland. Push it wider than Europe and the picture holds. Though here, the evidence changes character, and that distinction matters. In 2004, Douglas Rohde, Steve Olson, and Joseph Chang published a paper in Nature modeling common ancestry for the entire human species. Their conclusion was that the most recent common ancestor of every person alive today, one individual who sits somewhere in every single living family tree, lived within roughly the last 3,500 years. In their moderate migration scenario, the date came out as recently as the 1st century. That's a simulation, not an excavation. It depends on assumptions about how often people moved between continents, and the authors say so plainly. But the finding holds up under pressure. Cutting migration across the Bering Strait to a single person every 300 years moved the date by only a few centuries. Go back a few thousand years further, and the models reach a point with a strange, clean property. Every person alive at that moment is either an ancestor of every human on Earth today, or an ancestor of nobody at all. There's no middle category left. Now bring it back to the test in your hand, because this is where the two halves of your ancestry stop agreeing with each other. There are two entirely different things the word ancestor is doing, and consumer testing has quietly collapsed them into one. A genealogical ancestor is someone you descend from, a fact about history and paperwork. A genetic ancestor is someone who actually contributed a measurable piece of DNA to you. For your parents and grandparents, these are the same set of people. They stop being the same set surprisingly early. You inherit half your DNA from each parent, but you don't get a tidy half of each grandparent. Recombination cuts the genome into a limited number of chunks and deals them out. And the number of chunks doesn't double every generation the way the ancestors do. The ancestors grow exponentially. The chunks grow roughly in a straight line. One of those curves outruns the other very quickly. Graham-Coop's calculations put the crossover around the 8th generation. Past that point, it becomes unlikely that every one of your ancestors gave you anything at all. By 11 generations back, the early 1700s, well inside the range of a well-documented family tree, you carry DNA from fewer than half of your forebears. Read that carefully, because it is the sentence that changes what a pedigree chart is. Somewhere upward of half the real, documented, correctly researched people on the upper rows of your tree are your ancestors in history, in law, and in every meaningful human sense, and contributed nothing to your genome that any test on Earth could find. They aren't errors in your research, and they aren't people you failed to inherit from through some fault of method. The shuffling simply didn't route through them, and the shuffling is indifferent. Two things follow for the results page you may already have open. The first concerns your match list. A DNA match is a genetic relative, someone who shares a detectable segment with you. So your list isn't a list of your cousins. It's a list of the cousins the recombination happened to preserve a trace of. Real, verifiable third and fourth cousins go missing from it routinely, and their absence isn't evidence that the paper trail is wrong. Two people can be genuine cousins with a fully documented connecting line and share no measurable DNA whatsoever. The second concerns the percentages. An ethnicity estimate isn't a readout of your family tree, and it never was. It's comparison of your genome against reference panels of living people, and it can only report what the shuffling actually delivered to you. When the number moves after an update, it's the panel that's been refined, not your ancestry, and not your tree. Which leaves the question underneath all of this, the one that tends to arrive around row 30 of a chart somebody has spent a decade building. If the tree folds, and if everyone in a region converges on the same ancestors, and if half the names up there never touched your genome, what exactly has all that research been for? The mathematics answers that, and the answer runs opposite to the way it first sounds. What the collapse takes away is the idea that a tree extended far enough is a personal possession, that the far rows are yours. In some way they aren't anyone else's. Extended far enough, they aren't. Your 1,000-year ancestry and your neighbors are, to a very good approximation, the same set of people. What it hands back is more specific. Because everyone in a population converges on the same ancestral pool, the only thing that can distinguish one family's actual history from another's is the part DNA can't recover. Which of those people, in what order, doing what, and going where. A genome can tell you that you descend from medieval Europe. It can't tell you your fourth great-grandmother's name, that she was widowed at 31, or that she moved 200 miles with 4 children to a town where she knew no one. No test will ever return that. It exists in one place, in a record somebody wrote down, and only if someone goes and finds it. The DNA is the half everybody shares. The documented tree is the half that is genuinely yours, which makes the paperwork the rarer of the two, not the redundant one. There is a catch waiting on the other side of that, and anyone who takes this seriously runs into it fast. Once you know the upper rows of your chart contain enormous numbers of repeated people, you've got a research problem that no amount of care solves cleanly. The same ancestor sitting in 100 slots means the same document sitting behind 100 lines, and the standard software will happily let you enter them 100 separate times, building what looks like an enormous tree that's in fact one small population counted over and over. Untangling that means knowing which repetitions are real folds and which are your own duplication, in records that thin out at exactly the depth where the folding gets heavy. The people who do this well have a name for the moment they hit it, and a set of techniques for working through it. That is where this goes next. Before you go, what part of the world are you listening from?